In a factory in Kunshan, about an hour west of Shanghai, a machine is coating sheets of glass with a liquid. The glass moves through, gets dried, gets sealed. What comes out the other end is a working solar panel. Nothing in that process ever gets hot enough to glow. The silicon panels on roofs today begin life in a furnace at 1400 degrees. This one begins as a liquid, laid onto a surface roughly the way ink is laid onto paper. That factory switched on in June 2025. It's the first gigawatt scale plant in the world for this technology, and it cost around $700 million. Here's the number that made engineers pay attention. In 2009, the first solar cell ever made from this material converted 3.8% of sunlight into electricity. Worse than cells built in the 1950s. It was a curiosity. 17 years later, a Chinese lab reported nearly 28%. No solar technology in history has improved that fast, and the material isn't exotic. It's a crystal structure first identified in a Russian mountain range in 1839, ignored by the energy industry for 150 years. Start with the wall. Almost every solar panel on Earth is made of silicon. It works, and it survives on a roof for 25 years without much complaint. But it has a hard ceiling, and that ceiling isn't an engineering problem. It's physics. A single layer of silicon can never convert more than about 29% of the sunlight hitting it. Light with too little energy passes straight through the material. Light with too much wastes the excess is heat. The best silicon cells ever built sit around 27%. So the industry is now grinding out fractions of a percent against a wall it cannot move. And getting there is brutal. You melt raw silicon at over 1400 degrees Celsius, hotter than most lava, grow it into a single crystal ingot, then saw that ingot into wafers with diamond-coated wire. The sawing alone turns a large share of your silicon into dust. For decades there was no alternative because nothing else came close on efficiency, stability, and cost at once. Which brings us to the rock. In 1839, in Russia's Ural Mountains, a German mineralogist named Gustav Rose identified a new mineral and named it after a Russian collector, Lev Perovskite. For a century and a half, it stayed a geological footnote. And here's what trips most people up. The original rock barely matters. What matters is the shape its atoms sit in, a specific repeating crystal arrangement. Chemists worked out they could build entirely new compounds copying that arrangement out of cheap common ingredients plus a small amount of lead. And that pattern turns out to be extraordinarily good at one job. It absorbs light roughly 10 times more strongly than silicon does. That single fact changes everything downstream. A layer a few hundred nanometers thick, thinner than a soap bubble, absorbs about as much sunlight as a silicon wafer hundreds of times thicker. So you don't need the furnace. You dissolve the ingredients into a liquid, spread it onto a surface at low temperature, and let it crystallize. Temperatures stay under 150 degrees. There's no ingot to grow and nothing to saw, so most of what goes in actually comes out. But the thing that finally made the industry move isn't the one you'd expect. For years, engineers tried to make this material replace silicon. Then they stopped and asked a different question. What if it doesn't have to? Because the two materials absorb different parts of the spectrum. Perovskite is tuned for high-energy blue and green light. Silicon is better at the low-energy red and infrared that would otherwise pass straight through. So you stack them, perovskite on top, silicon underneath. Light hits the top layer, gets partly absorbed, and whatever it misses continues down into the silicon, which mops up the rest. That's a tandem cell. And because it captures a far wider slice of the spectrum, the ceiling climbs well past silicon's 29% toward a theoretical maximum somewhere in the 40s. The current certified record is 34.85% held by LONGi. Already comfortably past the wall, silicon can never cross, which is where China enters because a record cell is worthless if nobody can build it by the million. The Kunshan factory is run by GCL Optoelectronics. 1 gigawatt of annual capacity, a second gigawatt planned, 5 billion yuan invested. Its modules are the largest commercial perovskite panels made anywhere. In March 2026, GCL won what's reported as China's first commercial tandem module order, a 1.2 megawatt purchase by a research arm of China Huaneng. And that tender demanded something this technology had never faced: mass-producible, certified modules above 25% efficiency with a 25-year performance warranty. Hold on to those 25 years. It comes back, and not in a good way, before the rest of it. If you want more stories about the technologies that quietly decide who wins the next decade, subscribe and turn notifications on so the next one reaches you. Okay. In June 2026, Trina Solar certified an industrial-sized tandem module, 3.1 square meters, producing 907 watts at 29.2% efficiency, verified by TUVSUD. A normal rooftop panel today produces between 400 and 600 watts. Trina then sold them. The first commercial order went to a customer in New Zealand. And this is the part worth sitting with. China already dominates conventional solar to a degree that has no parallel in any other energy technology. In 2024, it produced around 93% of the world's polysilicon, 97% of wafers, and 86% of finished panels. Perovskite was, in principle, the reset, a technology that bypasses the furnaces and the ingots and the wire saws, bypasses exactly the capital-intensive infrastructure China spent 20 years and $50 billion building. A genuine chance for everyone else to start from level ground. Japanese and European companies are technologically competitive. That was never the problem. The problem is that the race stopped being about science and became about who can build factories and lock down supply chains fastest. That's the one race China has already run. Now the honest part, because three things complicate this. First, and this is the big one, perovskite degrades when exposed to moisture, heat, and ultraviolet light. The longest publicly reported operating data for these modules in real conditions is around 1,000 hours. That's about 6 weeks. And they're being sold with 25-year warranties. Modules are passing accelerated stress tests, but an accelerated test is a simulation. Nobody has 25 years of real rooftop data because the technology hasn't existed that long. Second, the lead. Most high-performing formulations contain a small amount of it, less than what's already in the solder inside conventional panels. But regulators in Europe are examining it. It's a solvable problem that hasn't been solved. Third, and almost nobody covering this mentions it, China's solar industry is in serious financial trouble. Manufacturing capacity sits at around 1,200 gigawatts against global demand of roughly 650. Average factory utilization last year was 44% for polysilicon. So this isn't a confident industry gliding into its next technology. It's an industry with more than half its capacity standing idle, betting on a new product to escape a price war it created itself. The trajectory still holds. The timeline is the part nobody should be confident about. For 70 years, getting more electricity out of sunlight meant refining one material against a ceiling nobody could move. Then a crystal pattern from an 1839 mineral, one that costs almost nothing and can be laid down like ink, went from under 4% to nearly 28% in 17 years and ended up stacked on top of the very material it was supposed to replace. The panels going up today aren't the end of that story, they're the substrate for it. So the real question isn't whether printed solar works, the labs have answered that, it's whether anyone outside one country will be in a position to build it.